Hi, in this course I teach the basic graph theory, and in today's lecture I will cover mainly complete graphs and bipartite graphs. If you are new to this channel, please consider subscribing my channel, and you may go through the previous lectures for the basic concepts on graph theory. Now we'll know what is complete graph. A complete graph is basically a graph in which each vertex is adjacent to all other vertices. What does it mean? So we'll discuss it through a example. So in this graph, say for example we are taking that there are three vertices. Okay, so these vertices say u, v and w. So this will be called a complete graph if each vertex of G, this graph is G, and so the vertex set of G is here u, v and w. So all the vertices will be adjacent to all other vertices. Okay, so each vertex will be adjacent to all other vertices. So for u, it will be adjacent to the other vertices, that is v and w. So u is adjacent to v and u is adjacent to w as well. Now for v also it will be adjacent to all other vertices, that is v will be adjacent to u and w. So if we write down this, so u will be adjacent to v. This is our notation for adjacency we have discussed earlier. So u is adjacent to v and u is adjacent to w also, and for v also we have that v is adjacent to u, which is the same thing as this one, and v is adjacent to w also. Okay, so now v is adjacent to w means this edge. Now we have for w, actually w is adjacent to u, that is the same thing as this u is adjacent to w. Okay, and also we have that w is adjacent to v, so w is adjacent to v is same thing as this one. So here we have basically the distinct edges are basically here this one u to v, that is u and v, that is this edge, and now u to w, that is this edge, and also we have another edge v to w, that is this one. Okay, so three edges. And what we have here basically that each vertex, we can see that each vertex of this graph is adjacent to all other vertices. Okay, so this is the graph G. Let us denote this G1. Okay, and we have a special notation for complete graphs, that is complete graph on n number of vertices is denoted by Kn. Okay, Kn, this one. Now so we can discuss another example. This example was basically for three vertices. Okay, so this was our K3, this was our K3. Now we'll discuss K4. Okay, so if we discuss more examples, the concepts will be clearer to us. So now we will discuss about K4. So basically as per the notation we can say that there will be four vertices. Okay, so let us denote u, v, w and x. Okay, so as per our definition of complete graph, so each vertex will be adjacent to all other vertices. Okay, so this u will be adjacent to what? U will be adjacent to v, u will be adjacent to w, and u will be adjacent to x. Okay, now we'll see the adjacencies of v. So here v is adjacent to w and v is already adjacent to u we have, and also v is adjacent to this x. Okay, now we'll see that the adjacencies of w. So w is already adjacent to u and v. Now w is also adjacent to x. Okay, now we'll see the adjacencies of x. So x is adjacent to u, v and w. So this is the K4 graph. Okay, if you have any doubt or query, or if you face any trouble to understand any of the concepts I teach through my videos, then you can comment on the respective video and I will definitely address those queries in probably the next lecture. Okay. So now we'll discuss about a complete graph on 5 vertices, that is K5. So it will be our last example on these concepts, complete graph. So for K5 we will have 5 vertices. Okay, so there must be 5 vertices and each vertex, so let us take A, B, C, D and E here. So this A is adjacent to 4 other vertices. Okay, so actually here we can observe that for each vertex it is adjacent to all other vertices. Okay, so if number of vertices be n, that is if the cardinality of the set of the vertex set of G be n, then for each vertex, okay, if V belongs to vertex set of G, that is if V be any vertex, then degree of V we can observe from the definition itself that degree of V must be n minus 1, because each vertex is actually adjacent to all other vertices. Okay, so since the number of vertices is n, so each vertex is adjacent to all other means the rest of n minus 1 vertices. Okay, so each vertex will have degree n minus 1. For example, here we can see that this A is adjacent to all other vertices, and here the number of vertices is 5, so A is adjacent to 4 other vertices. Okay, V, C, D and A, so the degree of A is 4. Similarly, degree of B is also 4, so B is adjacent to A, B is adjacent to E, adjacent to D and adjacent to C. Similarly, C is adjacent to A and B and also D and E. Similarly, D is adjacent to A, B, C and E, and also E is adjacent to all of A, B, C and D. So all the vertices have degree n minus 1 actually. So here we can have a remark like that. So we have a remark that in a complete graph on n vertices, that is in Kn, degree of each vertex is exactly n minus 1. Okay, so we have this remark. So actually in the previous class we had seen that maximum possible edges is possible only when each vertex have degree n minus 1, and actually today we have that this graph is exactly Kn, that is complete graph on n vertices, that is no more edge can be included to this graph with the condition that this graph has to be simple. Okay, this graph has to be simple because there is no multi-edge or no loop. So it is the maximal graph, so no other edge or no other edge can be included to this graph, such that this graph remains a simple graph. Okay, now we'll discuss about bipartite graphs. So the definition says that for any graph G, it is said to be a bipartite graph if the vertex set of G can be partitioned into two parts such that, say, V1 and V2, such that no two vertex of V1 or V2 are adjacent. That is, no two vertex of V1 are adjacent and no two vertex of V2 are adjacent. So we'll see through examples. So firstly we have to know what is partition. Okay, so let us take this set to be the vertex set. Okay, so here are 5 vertices in G. So the vertex set, say we have to name all the vertices, so A, B, C, D and E. Okay, so the vertex set is here, V of G is A, B, C, D and E. Okay, so here are 5 vertices, and firstly we have to partition this vertex set into two parts. Okay, so let us take for example, we are taking this partition, this to be a partition and this to be a partition. So it is V1 and it is V2. So we have to know firstly what is partition. So if a set, say A is a set, okay, and if G and H be two subsets of A, then we call that G comma H is a partition, is say called a partition sorry a partition of A if and only if these two conditions holds. Firstly, G union H has to be equal to A, and secondly, G intersection H has to be equal to empty set. That is, taking union of these two sets will have the whole vertex set. Okay, so if we take v1 and v2 to be the partition, then including the if we take the union of these two sets, then we'll get the whole vertex set v of G. Okay, and also these two sets has no vertex in common, that is their intersection is empty. So we can say that this actually holds because this vertex set was here A, B, C, D and E, and we have taken v1 to be A, B, C and v2 to be D and E. So these two sets have an empty intersection, and the union of these two sets is the whole vertex set. Okay, so we can take this partition, and now what more to hold, that no two vertex of the same part are adjacent, that is no two vertex of v1 are adjacent, that is A is not adjacent to A is not adjacent to B, A is not adjacent to C, and also B is not adjacent to C. Okay, and all other are already, like B is not adjacent to A, and C is not adjacent to A, and C is not adjacent to B. So basically these three conditions. Okay, and for v2 also, so for v1 we have these conditions, and for v2 also we have that this D and E are not adjacent. Okay, so D is not adjacent to E. So the only adjacency is here possible between these two partitions. So A can be adjacent to say B, or A can be adjacent to E also, and also say let's say C is adjacent to this D. Okay, so this may be a bipartite graph. So we will consider another bipartite graph. Okay, so it was our example 1. So let us say G1, this graph. Okay, and now we'll go to our example 2. So G2 is say this graph. So here we have say 4 vertices. Okay, so here 3 and here 1. So let us take this graph. Okay, so this vertex is adjacent to all of these vertices, but they are not adjacent to each other. Okay, so here the partitions are this is one partition and this is another partition. So this is also a bipartite graph. Now we can have another example, say G3 to be like a cycle. We are considering now a cycle, say this one, cycle on 4 vertices. We'll know later actually what a cycle, what is a cycle or something. So basically here we have taken a graph on 4 vertices, say. So now we'll check whether this graph is a bipartite graph or not. So it will be a bipartite graph if we can have a partition, so v1 and v2. So here we have vertices A, B, C and D. So if we can have a partition of this vertex set such that no two vertex of the same part are adjacent. Okay, so here the vertex set is, we have V of G is equal to A, B, C and D. So we can have v1 is equal to, so let us start with A. So B must not be there because B is adjacent to A. So a partition, no two vertex from the same part are adjacent. Okay, so B is not in v1. Also similarly D is not in v1. So let us check whether C can be there or not. So C is not adjacent to A. C is not adjacent to A. So C, let us take A and C to be apart. So here these two partitions are not adjacent. Similarly we can take v2 to be B and D. So B and D are not adjacent. Okay, so B and D are not adjacent because BD edge is not in this graph G. So we can take another part to be V and D, and we can now check that this is a bipartite graph because we can draw this same graph as A and C here, and B and D here, and A is adjacent to B, A is adjacent to B, B is adjacent to C, B is adjacent to C, and now C is adjacent to D, so C is adjacent to D here, and D is adjacent to A. So this is the graph basically. So it is this was the original graph, and it is another representation of the same graph. So these two graphs are basically same. Okay, so if we call this G4, so G4 and G3 are same graph on 4 vertices, and here only the representations are little bit different to notice, but they are same graphs. And here the partite sets are V1, that is A and C, this one, and also this one. Okay, so these two partite sets, and we have that this is a bipartite graph. Similarly, we can have another example. Now let us consider this example on say 6 vertices. Okay, so here we have 3, and here also we have 3 vertices, such that this one. Okay, so this is also a bipartite graph. Here let us take this to be A, B, C, and here D, E, and F. So here the vertex that is the partite sets are this one and this one. Okay, we can have another example like that, say on 5 vertices. Okay, and here we have that this adjacency, this is adjacent, and this is adjacent, and also this is adjacent. Okay, so it is also a bipartite graph, and here we can have this partition and this partition. Now actually here this graph we can consider another representation. Okay, so here the partite sets are, say this is A, B, and C, D, E, and F. So here the vertex set was originally V of G was A, B, C, D, E, and F. So 6 vertices were there, and we have taken here V1 to be A, B, and C, and V2 to be D, E, and F. Now check that this B vertex is actually a isolated vertex. This vertex is not adjacent to any of the vertices. Okay, so it is not adjacent to any vertex of the set V2 also. So by definition of bipartite graph, it is not B cannot be adjacent to A and C, but it is also not adjacent to any of D, E, F. Okay, so we can have another partite representation of this. So we can write it like that A and C here, and here we have the D, E, F, and also this B. Okay, so then we have that the adjacencies, A is adjacent to D, E, and F. So A is adjacent to D, E, and F, and this C is adjacent to E. Okay, so C is adjacent to E, and this B is adjacent to none of them. So we have here the partite set to be this one and this one. Okay, so we have here the partite set, say V3 to be A and C, and V4 as D, E, F, and B. Okay, so we can see from this example, this is an important example because say this is this was our G5 and G6, and it is G7. So here also G6 and G7 are the same graph. So here we have from this example that this partite representation, that is how we partition the vertex set and we form the bipartition. So it is not unique. Okay, so for the same graph we have different partite sets and different bipartition thing. Okay, so here we have the partite sets of cardinality both 3, and here we have 2 sets, one of cardinality 2 and another of cardinality 4. So this representation is always not unique. Okay, so in the next class we will discuss about multipartite graphs, that is there will be more partitions, so more than 2 partitions will be there, and also we will discuss about regular graphs. Thank you for watching my video, and Please like, comment and share if you like my video, and if you want more videos on graph theory. Thank you.